In section 4.4, we'll be discussing linear approximations and the second derivative test. So when you see the word linear, you should automatically think about lines, and so we're approximating graphs with lines. Specifically, we're talking about tangent lines. And so suppose we have a function f of x and its tangent line is drawn to a point a, f of a, like it is here. So we have this point of tangency, here's our tangent line. Then we're going to call that tangent line L of x. This equation here, it might look a little familiar. It's really just the point slope form of a line, just with some different things filled in for it there. So L of x is my function minus my y value of my point equals my derivative, which is my slope, times x minus the x value of that point. If I solve that for L of x, essentially just adding this f of a to the other side, I would get this equation f of a plus f prime of a times x minus a, or sometimes you'll see this at the end as well. And so the idea of a tangent line is that it can give us an approximation to our graph. And so, for example, if I want to find some point k, if I look here on my graph f of k, I can approximate it on my line and get the value L of k, and we can talk later about comparing those two values. But as long as I'm pretty close to this point of tangency, then my tangent line should give me a pretty good approximation of what that graph is. If I get too far away, like over here, it's not going to give me as good of an approximation. And so we call this a linear approximation. Whenever you see that, you automatically need to think about tangent lines. So when you see that linear, it's telling you tangent lines. So in example 1, we have a differentiable function f. It has the property that f of 5 is 3 and f prime of 5 is 4. And it asks us for the estimate for f of 4.8 using the local linear approximation for f at x equals 5. This word local just means nearby, so we're nearby 5. Linear approximation, telling me tangent line. So we start this out just by writing your tangent line, just like normal. We should be very familiar with this at this point. My tangent line is, so I've got my point here, and I've got my slope. So I can write my tangent line, y minus 3 equals 4 times x minus 5. So we should be really familiar with that. Our next step is we're just going to plug in that x value. So it's asking us to approximate f of 4.8. We're using the tangent line at x equals 5. So just pay attention. You're going to have one x value that it's asking you for the tangent line. Notice that matches up with those values there, and another that you're approximating. So I'm approximating at 4.8. So essentially, I can just plug that in for my x. And then I'm going to solve. And so essentially, I'm just going to add the 3 to the other side. You can put it at the beginning or the end. It's up to you. But this is an approximation, and so what I really want to write here is that f of 4.8, I'm going to use my approximately equal symbol, is 4 times 4.8 minus 5 plus 3. Now, I can leave my answer like that on a free response question. So I'll just put a note here. And you really do want to, even if you're allowed to use a calculator, leave it there, because it's very easy to make mistakes when I'm subtracting things with decimals, adding it, all of that stuff. Just leave it right there. But since this is a multiple choice question, we are going to want to simplify that. I would always recommend here subtracting first. You should get a small decimal here, and it'll make it easier than trying to distribute that 4. So we have 4 times negative 0.2, that's negative 0.8, plus 3. And so that gives me 2.2. That is my approximation for f at x equals 5. In number 2, it gives us selected values of the derivative of a function g. We know that g of 3 is 17. I'm going to highlight that. That's going to be important. It's asking me for the approximation for g of 3.2. Automatically, when I see that word approximation, I know I'm going to have to use my approximately equal symbol when I'm solving this. And it says using the line tangent, that's important, to the graph at x equals 3. So it's important here to notice that this is at x equals 3. that's the point I want to use, and that's the slope I want to use. So my point is already given to me, and I have to have that because I'm only given my derivative here. I have to have my y value from somewhere, so that's given. My slope for my tangent line equation is going to be g prime of 3. So again, I'm noticing that I'm looking at x equals 3 because it tells me that's where my tangent line is. Don't get confused and think you want 3.2 because that's asking for the approximation. Okay, so use the x value for the tangent line. So I see that is negative 1.2. And now I can write my tangent line equation. Y minus my y value from my point, 17, equals my slope, negative 1.2, that was my derivative, times x minus 3. Now, if all I was asked to find was the tangent line equation, I would be done. However, I was asked for the approximation for g of 3.2, so I'm going to go ahead and plug in y minus 17 equals negative 1.2 times 3.2 minus 3. Even though this is an open-ended or free response problem, I cannot leave my answer here. I want to solve for this y so that I can get that approximation for g of 3.2. So I'm going to solve. And you don't even have to simplify all the way, but I'm replacing my y with g of 3.2. That's the value I'm approximating. Is approximately equal to everything I had on the right side. And then don't forget to add that 17 over. So right here, this would get me full credit on the AP exam on an FRQ. If you want to simplify, you could go ahead and you would get, 16.76 would be your answer. So often we're concerned about whether our approximation is an underestimate or an overestimate. And so it's hard for us to know that without knowing the exact original function, but we can still use derivatives to help us, and we'll actually use the second derivative to determine if our value is an over approximation or an under approximation. So if our graph is concave up, like these graphs on the left, then the tangent line is below the graph, which gives me an under approximation. So f is concave up, that means that f double prime is positive. So if f double prime is positive, then I have an under approximation. So concave up is an under approximation. Concave down, my tangent line would be above my graph, and so that will give me an over approximation or an overestimate. So again, concave down is f double prime is less than 0, will give me an over approximation. It might seem a little backwards that positive gives you an under approximation, negative gives you an over approximation, but you really just have to think about the graphs. If my graph is concave up, my line is below, so it's an under approximation. Concave down, my line is above, it's an over approximation. When you're justifying these answers though, it's not enough to just be concave up or down at the point of tangency. I actually have to look between the point of tangency and whatever value I'm approximating over here. So you'll see we'll use some intervals in our explanations. So number 3, we have a function f of x, which is 3x to the 1/5. It asks for the approximation for f of negative 0.85 using the line tangent. So I see that word tangent, I know what I need to do to the graph of f at x equals -1. That's my point of tangency. And then it also asks me, is this an under approximation or an over approximation? So I know when I see that, I'm going to have to think about the second derivative as well as the first derivative. So things I need to know to find the tangent line: point and slope. So for my point, I know my x value is -1. I'm going to plug that into my original equation, f of x. Now that 1/5 means 5th root of -1. Since that's odd, it will just be -1, so this is -3. For the slope, I will need to find f prime of x first. So that would be 3/5 x to the -4/5. And then I will also need to find f prime of -1. So specifically at that point, -1, 3/5 times -1 to the -4/5. Now that negative really just means I'm in the denominator, but because this is -1 to the 4/5, that means I take the fifth root and then take it to the fourth power. So that will be positive 1 because I'm taking it to an even power. So this will just be positive 3/5. And so now I can write my tangent line equation. Y plus 3 equals 3/5 times x plus 1 minus -1. I still need to write my approximation though. And so f of -0.85 is approximately 3/5 of -0.85 plus 1 minus 3. I can leave my answer right there. I do not need to simplify it on these open-ended problems. You can see it could get a little messy here with fractions and decimals and negatives, all of that. So we just want to leave it right there. So we answered this first part. What is the approximation? And then the second question is this an under approximation or an over approximation? So when I see that, again, I have to be thinking about the second derivative. So I will need to find the second derivative. Our first derivative was 3/5 x to the -4/5. So our second derivative will just be the derivative of that, -12 over 25 x to the -9/5. And so in order to decide if this is positive or negative, we might want to rewrite this as a fraction. Now this x to the 9/5, those are both odd numbers, which means this could be positive or negative. Pay attention to our x value. It was x equals -1. So if I'm plugging in numbers like -1 or numbers nearby -1, essentially less than 0, this piece right here, the x to the 9/5 would be negative. So overall, it would be positive because of the -12. So it would be negative over negative, that's positive. So for our justification, we're going to say when x is less than 0, you could give a smaller interval like between 0 and -1 or something that contains both -1 and -0.85. So x less than 0 definitely covers that. So when x is less than 0, f double prime of x is greater than 0. This is positive. So this approximation is okay, and so remember here, greater than 0 means my graph is concave up, tangent line is below my graph, so this is going to be an under approximation or underestimate, either one is okay. Number 4, it tells us that we have a function f, and it tells us our slope, dy dx equals 1/2 x minus 1/4 y squared. So our original function is probably implicitly defined looking at that derivative. We have the point 1, -2, that's important. And it tells us that our graph is concave up on that interval from 1 to 1.5. It asks us, or it tells us that k is the approximation for f of 1.3. And it says found using the locally linear approximation of f at x equals 1. So whenever you see that, that just means tangent. It's just a fancy word for tangent. Which of the following statements about k is true? So there's a lot going on here. That k is just f of 1.3. So it's asking me to approximate f of 1.3 and then also decide if this is an over approximation or an under approximation because I see those as my options. So automatically, since my graph is concave up, like we just talked about in the problem up above, concave up means my tangent line is an underestimate for my graph. So I know that my answer cannot be B or D because those have overestimates. So it's either A or C. So the other part I need to find is what is that approximation actually. So we have our point. The other thing I need to know for my tangent line is my slope. So I'm going to need to plug that point into my derivative. What's different here is that I have an x and a y in my derivative, so I have to plug them both in. Remember that the way I write that is to say dy dx and then my evaluation bar and then the point. So I have 1/2 times x equals 1 minus 1/4, x was -2 squared. So this is 1/2 minus 1, which is -1/2. So that's my slope. So now I can write my tangent line y plus 2 equals -1/2 times x minus 1. Again, I'm using that 0.1, -2. Now the 1.3 is going to come into play. I don't use that until after I've already found my tangent line. Also, it did tell me local linear approximation at x equals 1. So that tells me where my tangent line should be. So my approximation, I'm going to plug in 1.3 for x and simplify. So f of 1.3 is approximately -1/2 times 0.3 minus 2. So half of 0.3 is -0.15 minus 2 is -2.15. And so my answer here is C.